Welcome, everyone. My name is Hima Lakkaraju. I'm excited to be here to moderate this talk and discussion today. Today's speaker will be Professor Cynthia Rudin from Duke University. So there's going to be a lot of exciting things to talk about interpretability and explainability. Before we get into the logistics of today's talk, I just want to mention that this talk is being both recorded and live streamed. So if you prefer not to be in this talk, feel free to exit the Zoom call and open the YouTube live stream and watch the talk there. But after 1 p.m., we will not be recording the participant-driven discussion anymore. At that point, you can join back on the Zoom call for the discussion, right? So the agenda for today would be from 12 to 1 p.m. ET, we'll have the talk and the Q&A. From 1 to 1:05 p.m. ET, we'll have a short break. From 1:05 to 1:30 p.m. ET, we'll have a participant-driven discussion where all of you will get a chance to discuss about today's talk and more broadly about the field of trustworthy ML. Okay. All right, before we get into the details of today's talk, just wanted to say a couple of lines about us. So we are the Trustworthy ML Initiative. For those of you who are new for this particular talk or new on our community, welcome here. So here is all our amazing smiling faces of all the organizers and our awesome advisors. We have started this initiative with the following goals, which is to provide easy access to fundamental resources, to provide a platform for early career researchers, to encourage discussion and debate on various topics of trustworthy ML, and to create a community of researchers and practitioners working on this topic. To this end, we have curated a bunch of tutorials, courses, papers on these topics. Please feel free to check our website to see these. We also organize on a regular basis Rising Star Spotlight talks to support and promote younger researchers in the field and also highlight them on our Twitter channel. We also have a very active Twitter feed and channel going on, so feel free to tag us when you discuss your work or when you try to disseminate your work on Twitter. And apart from that, we are conducting a bunch of symposiums and workshops as well on the topic. So thank you again for joining us today for this talk. Okay. Again, the rough agenda for today's talk is 12 to 12:45 p.m. would be the talk itself. Please do submit your questions on the Q&A tool throughout the talk. Most likely the speaker will be taking questions towards the end of the talk, but the speaker may also choose to pause at some points in between the talk and take some questions at that point. But please do submit all your questions on the Zoom Q&A tool. Others feel free to upvote the questions, comment on the questions and so on, but please use the Q&A tool. And from 12:45 to 1 p.m., we'll ask the speaker some questions about her research journey and why she picked to work on this field and what excites her about this field and so on. So you'll get to know a lot about the speaker and Cynthia's thought processes. From 1 to 1:05 p.m., we have a short break. From 1:05 to 1:30 p.m., there'll be our usual participant-driven discussion. Okay. All right, so with that, it is my real pleasure to introduce to you all Professor Cynthia Rudin, who is a professor of computer science, electrical and electronics engineering and statistical science at Duke University. Cynthia directs the Prediction Analysis Lab, whose main focus is interpretable machine learning. Previously, Cynthia held positions at MIT, Columbia, and NYU. She holds an undergraduate degree from University of Buffalo and a PhD from Princeton University. She is a 3-time winner of the Informs Innovative Applications in Analytics Award and a fellow of the American Statistical Association and the Institute of Mathematical Statistics. So I think it is every one of us here, or most of us at least here, can fairly agree that Cynthia has been a pioneer in the area of interpretability and explainability. She has been working on this area long time before, since this became a fad and a lot of other researchers started jumping on it. So she is really considered as one of the experts in this field and one of the most leading researchers. I was very fortunate to get to work with her at some points in my career, at least. And yeah, I'm super excited to present to you all Cynthia Rudin, who is one of my favorite researchers. Cynthia, over to you.
You're one of my favorite researchers too. Thanks, Hima. All right, I'm going to share my screen here. There we go. Great. Okay. Cool. So I've worked on a lot of machine learning problems, and I found that it's pretty easy to notice that very often simple yet accurate models are likely to exist. And this has huge implications for trustworthiness of machine learning models. And I wanted to know why and when that happens. So I want to start with an example of what I'm talking about when I say a simple model. Okay, so I'm going to start with an example that this is a collaboration that I've been working on for several years, where if you have let's say you have a patient, and let's say that the patient has an aneurysm, and this is a blood vessel in your brain, it bursts, you have a hemorrhage in your brain, there's blood in your brain, you go to the hospital, you get surgery, and they replace this, they fix you up, they put you in the intensive care unit, and they put continuous EEG monitors on you. And the people I work with they're watching these monitors to see whether these people are likely to get a seizure. And these are subclinical seizures, so the patients are not shaking or anything. The only way you can tell whether the patient's having a seizure is based on the signals from their brain. Okay. So I've been working with these neurologists for quite a while, and what they've told me is that these seizures are very common. The seizures cause brain damage. The seizures can actually cause more damage than the actual injury that the patient had, and you need EEG to detect seizures. But the problem is that these EEG monitors are expensive and they're not well utilized. Like the doctors, there's not enough monitors, not enough doctors to go around, and so the monitors sit on people for way too long who don't need them, and then the people who really need them, they don't necessarily get them. And so we wanted to predict seizures in advance to determine, how long a patient really needs to stay on these monitors so that they can be moved, the monitors can be moved to someone else. So using data from the Critical Care EEG Monitoring Research Consortium that my collaborator leads, we developed a medical scoring system called the 2 helps 2B score. And 2 helps 2B looks like this. It's so simple that I can put it on a PowerPoint slide. And it's 2 helps 2 because it's 2 HELPS and then 2 points for the B. And then the total score that the patient gets based on their EEG measurements gets translated into a risk of seizure in the next 6 hours. Now, the interesting things about this score is that it's just as accurate as a black box model in this data set. It doesn't force you to trust it like a black box model. Doctors can decide themselves whether to trust it. There's nobody forcing them to use it. And this has so far led to a substantial reduction in the duration of EEG monitoring per patient, which allowed the doctors to monitor 2.82 times more patients. And so it's been able to help the doctors save lives and reduce brain damage, which is really, really important. And it's now used in several hospitals. Now, this model is a simple model. It's a sparse linear model with integer coefficients. It is the solution to a mixed integer nonlinear program, and it was solved with a machine learning algorithm called the lattice cutting plane algorithm. So, okay, so great. So that's what I mean by a simple model, but we don't always use simple models when we need to. In fact, I think that perhaps we're using complicated models when we don't need them. And you probably all know the COMPASS example by now. COMPASS, of course, is a proprietary model that's used in the US justice system that's caused a lot of controversy. And COMPASS was designed by a company that has lots of data, right? They collect over 130 pieces of information to produce a COMPASS assessment. And so we were wondering when this data set came out how accurate COMPASS actually was. And we used some data from Florida to try to figure that out. This is the ProPublica Florida data set, the famous one. So when this data set came out, we immediately compared COMPASS's accuracy on 2-year recidivism prediction to the accuracy of our latest machine learning method in the lab at the time, which is a sparse decision tree method called Corals. And we sent the Florida data into Corals, and it produced this machine learning model that was so tiny that it fits on the bottom of a PowerPoint slide. And we looked at this thing and thought, okay, well, that's pretty simple, right? This is an optimal decision list on this data set. And we were comparing it to this black box that's used in the justice system. And we thought, okay, how accurate is this? And the answer is they were both equally accurate. The different colors are from different folds of the data. And Corals produced essentially that same model that I just showed you across folds, and the accuracies are essentially the same. But not only do these two models perform the same, as it turns out, when we applied the whole arsenal of machine learning techniques to the problem, we got very similar performance across algorithms. And some of these algorithms produce very complicated models, like boosted decision trees or random forest or something like that. Whereas, our model is so tiny that it fits in the bottom of that slide there. And so, the truth is, we were debating about algorithmic fairness of Compass for years, but the truth is we just don't seem to need Compass at all, right? Why do we need this complicated model? Why do we need this proprietary model? So, why are we still using it? Okay, so as far as I can tell, there's really no benefit from complicated models for rearrest prediction in criminal justice. So there's no need for complicated models there. But as I mentioned, I've worked on a lot of machine learning problems, including all of these problems, and I haven't found that any of them required a complicated model. So all of them were solved with very simple models. But it depends on your data representation, because if you're doing computer vision, then you need a neural network, because neural networks are really great for creating a good data representation when you don't have one. But if your data naturally come with a good data representation, like in all of these problems that I'm showing you here, then all the algorithms tend to perform the same. So let's say that we're doing supervised learning, where we want to minimize the loss function to make our models more accurate. Okay, so you minimize loss. This is standard supervised learning. And then if you want to make your model simpler, you have to limit the complexity of the model. So then you'd solve a constrained optimization problem, right? You want to minimize loss, keep the model accurate, but also keep it less complex. Now, as soon as you add this complexity constraint, the problem becomes much harder. Like the optimization problem computationally becomes much harder. And so, if this problem can be solved with an accurate decision tree, you'd have to solve for an accurate and sparse decision tree, which of course is much harder. And we know that it's not that difficult to get a decently accurate decision tree. We can just use CART for that. But if we want the decision tree to be accurate but also sparse, then we need a specialized algorithm. And I'm just showing you here a result from the GHOST algorithm from my lab. GHOST is where we've gotten since corals in the last few years. But GHOST produces these very sparse, accurate decision trees. And this tree for the same data set, this is actually more accurate than the CART model, but it's optimized very, very heavily. Now, if we're talking about, say, accurate linear models, well, we know how to do that, right? We can use logistic regression. But then if we want it to be sparse, like the 2 helps 2b score, we have to actually optimize for it, that sparsity, and that becomes much harder. What if we just throw the most complexity we have at the problem? Like, let's just use our favorite neural network or boosted decision tree. So the question I want to ask is whether we can get the same level of accuracy if we use a very sparse model, like a very simple model, like a sparse decision tree or a sparse linear model. So in other words, I want to know whether the accuracy of these two things is equal, right? Even if we add the constraints, can I do that without wrecking accuracy? And I want to know whether or not these things might be equal to each other before solving the harder constrained optimization problem. Okay, so in other words, can I determine the existence of a simple accurate model without actually finding one? So before I go to the trouble of optimizing, can I know that it exists? Okay, so in this talk, I'm going to try to figure out the answer to that problem, right? What in the world would cause there to be simple models with the same accuracy as complicated models for most problems? And I have a theory, and that theory is going to allow me to define a condition under which a simple yet accurate model is likely to exist. And that condition is that the Rashomon set is large. Okay, so I will tell you what that is in just a minute. So this is the paper I'm talking about. And it's a study in Rashomon curves and volumes. It's a new perspective on generalization and model simplicity in machine learning. Okay, so what is this condition? And so the condition is simply that there are a lot of good models. Okay, so another way to say that is that the true Rashomon set is large. Okay, so the true Rashomon set is the set of models with low true loss. So if I plot abstract hypothesis space on this axis, and then this is my loss function, the set of good models is the Rashomon set. So it's the set of models with low loss. Okay, so I'll write it this way. It's the set of models from my class such that the expected loss is low. All right, and I claim that if the true Rashomon set is large, if there are a lot of good models, then a simple yet accurate model is likely to exist. So it's kind of like this, like a big ocean theory, right? So the bigger the ocean, right, the higher the chances are that you'll find a big fish in there somewhere. And the larger the Rashomon set is, the larger the chance that you could find a simple function in there somewhere. Like there's so many good models that hopefully at least one of them is simple. Okay, so great. Now in the paper, we have a large amount of theory, which sort of shows you why this might occur fairly often, and very simple cases in which it occurs and so on. And then we have some experiments and observations. Unfortunately for you guys, or maybe fortunately for you, I don't really have time to go through all of this, so I decided to ditch the theory and just talk about the experiments in the paper. Okay, so I wanted to know, what Rashomon ratios look like in reality. So the Rashomon ratio it's a fraction of models that are good. Okay, so I've been, my theory here is that if you have a lot of good models, then at least some of them will be simple. Okay, so I'm going to do an experiment where I'm going to correlate the number of good models, or the fraction of models that are good, with whether or not we have the potential to have simpler models that are good. Okay, so I'm going to look at this Rashomon ratio. This is called the empirical Rashomon ratio because it's just the fraction of models we measure that are good on our data set. And normally you wouldn't calculate this because you'd have to actually calculate the number of all models and then a fraction of those that are good. But usually we're dealing with very large hypothesis spaces or even infinite ones, and so you can't actually calculate this. But I'm going to do it today for the purpose of science. It's a very expensive experiment that I'm going to describe here because it requires a lot of computation. And luckily, what we found out in this experiment means that we don't have to calculate the Rashomon ratio in reality to gain practical insight from it. Okay, so here's our experiment. I'm gonna look for the correlation between two quantities. The first is the size of the Rashomon set, and the second is performance across different algorithms, some of which produce simpler models. Okay, so I'm going to calculate the size of the empirical Rashomon set using decision trees of depth 7. Why decision trees of depth 7? It's because they can be sampled. Right? Depth 7 trees, I claim they serve as a good approximating set for a larger function space that includes lots of different functions because they're able to fit our data sets. So in other words, I want you to think about a big function space, and that function space includes all decision trees, all support vector machine models, all boosted decision tree models, random forest models. So it's a big space of functions. And I claim that this function space, okay, with its Rashomon set, right, this is the set of good models in there, I claim that set can be nicely covered by decision trees of depth 7. Okay, so this is all decision trees of depth 7, and I claim it's a good cover for the space. And so if I look at the ratio of decision trees that are good to the number of decision trees that are good compared to the total number of decision trees I sample, that's going to give me an estimate for the Rashomon ratio. Okay, so that's one thing I'm calculating. And the other thing I'm calculating is the performance across different machine learning methods. Do all the methods perform similarly, and do they generalize? Because I want to know if all of the different methods are producing different models within the same giant Rashomon set. And if they all perform the same, including like CART and logistic regression, then it means we're producing very diverse models, all different levels of complexity within the same Rashomon set. And my goal is to determine whether these things are correlated with each other. Okay, so I hope the experiment is clear. I want to know if there's a lot of good models and if that correlates with good performance or similar performance across algorithms, okay? Great, so I'm going to tell you the results of the experiment and then I'm going to show you some more details. So the result is that when the Rashomon ratio is measured to be large by the decision trees, then all the methods tend to perform similarly and they tend to generalize well. Okay, so what I'm seeing is exactly what my theory says. It says if the Rashomon set is large, if there's a lot of good models, then all these different machine learning methods tend to perform similarly and they tend to generalize. And so that kind of opens the door for simple models. All right, so let me show you the details on this. The reverse, by the way, is not always true, and I think that's an artifact of the way I'm measuring the Rashomon set. But that was interesting. We weren't expecting that. Okay, so cool. So yeah, let me show you some results. This is results on. I'll just start with a few data sets. We did this for 64 data sets. All right. So when the Rashomon ratio is large, then you get results like this. This is 4 different data sets, 5 different machine learning methods, training and test, and you see everything is the same, right? It's just the same. So CART is performing the same way as gradient boosted trees on these data sets with the large Rashomon sets. And then when there was a small Rashomon ratio, we didn't see the same thing. So sometimes you'd see results like this where some of the methods would perform better than others. And you wouldn't generalize as well between training and test, like over here. Sometimes everything performed fine. Sometimes it was just like the large Rashomon case, but I think that this might be an artifact of the way that we're measuring the Rashomon ratio. I think we're measuring it in a way that it could seem smaller than it actually is. But in any case, we have our nice result that a large Rashomon set leads to fairly uniform performance across algorithms and good generalization. So if you can't measure the Rashomon ratio in practice, which most of the time you can't, then that's okay because our results tell you something. They tell you that if the Rashomon ratio is large, all the methods perform similarly and they generalize well. And if the methods perform differently, it's likely you're in a case where you have a small Rashomon ratio. And now we're not completely sure about all of this yet, but it certainly is a viable possible explanation for what's going on and kind of why me and a lot of other people have found that many algorithms perform similarly across many problems. So why do simple models perform well? It's possibly because there's a large Rashomon ratio. Okay, so this experiment really gave us a lot of insight into the secret existence of simpler models. So let me just pause here to answer a question, it looks like. Yeah. Okay, I'm very curious to understand why decision trees and especially depth 7 can cover the set of all models. Why depth 7 and not depth 9? Why decision trees and not 2-layer neural networks? Okay, so we could have used 2-layer neural networks. We just couldn't sample as well from 2-layer neural networks. Why did we use depth 7? It's because they can fit all of the, we used 64 different data sets, and we found that depth 7 was good enough to fit the data sets without overfitting too much. And if we tried to use depth 9, the Rashomon ratios would be much, much harder to compute. As it is, the Rashomon ratios are hard to compute because the size of depth 7 decision trees, right, the size of that set is absolutely enormous. So being able to sample that, we needed a function space that we could sample from. And decision trees are actually really easy to sample from because you can just build the tree in lots of different ways. It's very easy to sample from it. But we could have used something like neural networks. That would have been okay too. Decision trees have some major advantages over other methods. First of all, they're completely robust to outliers. They handle multi-class problems. They're non-parametric, so they're actually very flexible and very powerful. So that's why we chose depth 7 trees. But yeah, somebody could definitely repeat this experiment if they wanted to with another function class. And I'm guessing you'll get the same result, but I'm not sure about that. And I'm curious to find out. Okay, can you estimate the Rashomon ratio before analyzing a data set? That is a good question. Okay, so and that's where I'm going with this talk. So thank you for asking that. I'm going to delay the answer to the question for a few more slides, and then I will answer that then. Okay, cool. So I want to tell you about something else besides what I just showed you, which is something that we call the Rashomon curve. And we weren't expecting to see this curve, but we found it on every single data set that we worked with. Now, the Rashomon curve is it's the Rashomon ratio versus the empirical risk, or the best empirical risk over each function class. And when I'm going to plot a whole bunch of points on this curve, and F1, the simplest function class, is going to be like decision trees of depth 1. And then this is going to be depth 2, depth 3. So these are a bunch of embedded function spaces here. Now, what's going to happen as we increase complexity of our function spaces? Well, what's going to happen is, first of all, we're able to model data better. So our empirical risk is going to go down, okay? Because we can just fit the data better because we have more complex function classes. And then it's not really clear what's going to happen to the Rashomon ratio when you do this, because the numerator and the denominator both go up, right? The numerator is the count of functions with low loss, and the denominator is the total number of functions, and both of them go up as you increase complexity. So as it turns out, it does something kind of funky. It actually goes down, but it goes down in this weird way. So as it turns out, when you start with the simplest function classes, then the empirical risk can be decreased without really changing the Rashomon ratio. But then all of a sudden it like nosedives, like it just goes straight down. The Rashomon ratio gets really tiny really quickly. And sometimes you'll see a little overfitting, like it might go a little bit left, but most of the time it just goes down so quickly that you don't even see the overfitting, okay? So yeah, we found this on all different data sets, and sometimes you see the whole curve, but sometimes it just goes straight down. Like if decision trees of depth 1 are good already, then you don't really change accuracy when you add more functions, right? So we really saw this quite across data sets. So here's 3 examples where we saw the whole full curve, and here's 3 examples where it just went straight down. Now that's the training set. What about the test set? Statistical learning theory tells us what should happen on the test set. It says that you generalize better for smaller function classes than you do for larger function classes. So what we expect to see is something like this, where for these really big function classes, you overfit, and for the really small function classes, you perform well. And it kind of indicates that the best performance should be right here around what we call the Rashomon elbow, where you're getting, excellent empirical performance, right? Good empirical risk, but you also have a low complexity class so that you can generalize well. So the elbow here seems to be a good choice for model selection. And I just want to show you the results of the experiments. I'm going to show you all 64 data sets here. And the results look kind of like this. And as you can see, in every single figure, there's a Rashomon curve, right? Either across and down or just straight down. And this, by the way, is averaged over 10-fold to produce all these curves for both training and test empirical risks, as well as Rashomon ratios. So this is a really expensive experiment. And I'm going to zoom into some of these curves so you can see what's going on. Okay, so sometimes we get exactly what we kind of thought we would get, where, here's a case where we're generalizing better for the small function classes, the best models at the elbow. It's kind of exactly what you expect. Same thing here, best models at the elbow. Sometimes we always generalize, like if we have a lot of data, sometimes we'll always generalize. And then sometimes we never generalize when we don't have enough data, but that's the nature of statistics. But not in any case, the elbow seems to always be kind of a good place to be, because it gives it gives you good performance, and it gives you the simplest models with good performance. Okay, great. Yeah, so the elbow model always seems to be a good choice for model selection. So back to the question that I got here. So the elbow seems to be a good place to be, but in real problems, you don't actually know what the Rashomon ratio is, and you can't measure it. You can't even measure a single point on it. And so you kind of want to figure out where you are on this curve to figure out how to get to the elbow, but you don't know where you are. You can't even measure a single point on the curve. So what do? So I claim that what you can do is you can try a lot of different machine learning methods on the data set, because we know that different machine learning methods right, have different levels of complexity. And so here, if you have different models that are different levels of complexity and the empirical risk is changing, then you're probably on this part of the curve, right, where you could increase complexity and move yourself toward the elbow. Okay, so you've got the algorithms performing differently. And then over here, if you're on this part of the curve, the different machine learning algorithms, which produce different levels of complexity, they would all perform very similarly, right? They have this similar empirical risk, but different Rashomon ratios, different levels of complexity. Okay, so in that case, you could potentially try to reduce your complexity and move up toward the elbow and produce a nice, simpler model. So I've been thinking that this kind of might explain some of the things that me and others have been observing across platforms and across data sets, right? There are some problems like ImageNet, where the field has been designing more and more complicated models, and it reduces the error. So maybe we're still on like the top part of the Rashomon curve. And on the other hand, you might want to consider problems like MNIST, where you're already at 100% accuracy. And then in that case, maybe we should be aiming for simpler models that might have other properties like interpretability, and they might generalize better outside of MNIST. They might be more trustworthy. And then there's a ton of problems like the kind I usually work on, where it doesn't matter which machine learning algorithm you pick, they all perform the same. Like, for the rearrest data from Florida that I was telling you about, right? It doesn't, even if you add loads more complexity, you're just going to overfit the data set. You're not going to get any more accurate. And so for these types of problems, we might want to walk kind of up the curve and try to lower complexity and walk up toward the elbow. So what I'm saying is that I can give you an easy check for the possible presence of a simpler yet accurate model. And that check is to pick several of your favorite machine learning methods, run them all in the data. If they all perform differently, then the model class might be too small to include the elbow solution. So you probably want to use more complex models. Whereas if you run these algorithms and they all perform the same, like in the earlier examples I was telling you about, like the compass example, your model class might be larger than necessary, and you could get away with a simpler model. So you can decrease complexity. So, I really like this analysis because you're essentially benefiting from kind of knowing or inferring the size of the Rashomon set without ever having to calculate it. And like I said, it's just a theory, but I think it's a reasonable explanation of what could be going on in problems like rearrest prediction. So we've been wondering if you could kind of write down or visualize the Rashomon set, and how would you do that, and what space should you use to do it? So in a recent paper, we proposed to use a space of variable importance on the axes. Okay, so the paper is called Exploring the Cloud of Variable Importance for the Set of All Good Models. What we propose in this paper is to consider each model as being a point in variable importance space. So on the axes are the importance of the different variables. Here we're using permutation importance, but you could use a different type of importance if you like. And then we're looking at the cloud of models that are all good, okay? So in this case over here, if variable 1 is important, as it turns out, variable 2 has to be less important in order for the model to be performing well, okay? So there's like this inverse relationship. Model 1 is important, that means, variable 1 is important, that means variable 2 is less important, and vice versa. So we were wondering how that would look for recidivism, right? How important are race, age, and gender to all good logistic regression models on the Florida data, right? If age becomes more important in a good model, does race need to become less important? And when I say good, I'm just meaning low loss. I'm not talking about using it in practice or anything like that. So we created what we call a variable importance diagram for the COMPAS data set. Now, each dot in this plot is a well-performing logistic regression model on that COMPAS data set. And the axes measure the importance of variables. 1 means not important. 1.10 means that the error would increase by 10% if we messed up the variable. So 1.10, that means the variable is really important, okay? And what you can see from looking at this plot is that that there are models that exist for this data set where priors and age can both be important, but they don't need to be. Like you can have a model where prior and age are both not important. And you can have a model where race is important, but it doesn't need to be. Like you can have also a model where race is not important at all. And in fact, to be honest, race is really just not important for recidivism prediction because it's correlated with age and number of priors, which are, they're correlated with race due to systemic problems in society and systemic racism. So the addition of the race variable generally doesn't actually help you, although you could create a model that uses race if you wanted to. Not sure why you'd want to do that. Maybe for some social services reason, I'm not sure. In any case, what we found was that models that use prior offenses very heavily don't use race very much because of that correlation. Okay, so in summary, I've defined a condition under which a simple yet accurate model is likely to exist, which is that the Rashomon set is large. And I showed a simple check for large Rashomon sets, which is that all different machine learning methods perform similarly. And I introduced Rashomon curves and variable importance diagrams for helping us understand the set of good models for a given data set. So, and the Rashomon curves, interestingly, seem to occur in all the data sets we considered, and they help us to understand why different problems seem to behave differently in machine learning. Okay, so now that we know that interpretable yet accurate models are likely to exist, we can go and find them. And that's what my lab works on. So finally, at the very end of the talk, I get to introduce myself. So my lab works on very sparse models. And you've seen already the corals and ghost algorithms that produce these decision trees. And you've also seen the model, that the 2 helps 2b score that was produced by our algorithm for producing scoring systems. I also work on interpretable neural networks for computer vision problems, where the definition of interpretability does not involve sparsity. I also work on data visualization and dimension reduction, and almost exact matching for causal inference, where we're trying to match treatment and control units as closely as possible to mimic a controlled experiment with observational data. And then this is, of course, the last topic that I've just talked about during this lecture. All right, thank you very much.
Okay. Awesome. Thank you so much, Cynthia, for this amazing talk. I will just look to see if there are any more questions. So Andre has a question. So can you estimate the Rashomon ratio before analyzing a data set?
Yeah, so that was a very smart question that was asked before I explained how to do that, right? Yeah. So you can look at lots of different machine learning methods and try them all out, and if they all perform similarly, it could be because you have a large Rashomon ratio.
Yeah. And Jesseline has posted a question, I think, on the chat to panelists, in which Jesseline is asking, in your example, are prior offenses a proxy for race if taking into account systemic racism?
Yes, partly. Partly.
All right. Okay. So I think, given that we have looked at the questions, so maybe we'll get into like knowing more about Cynthia's like thought process about research and so on. Others feel free to keep posting questions so that we can also include them as we discuss. So I see one more question from Vishal K. How Rashomon ratio is determined, how a model is determined to be good? Okay, there are a bunch of questions coming up. So
okay. Yeah, so how's the Rashomon ratio determined? Okay, so the Rashomon ratio is determined the way we measured it in the experiment was we sampled from the set of decision trees of depth 7, and the fraction of them that had low loss is the Rashomon ratio. Okay, and then where's the rest of that question? How's a model determined to be good? It's just if it has low loss, right? If it's in the Rashomon set.
Okay. And David has another question, which is when trying a bunch of different ML models for Rashomon curve estimate, do you need to hyperparameter tune each model or use default settings?
So there's no hyperparameter tuning because we're not actually fitting data, we're just sampling models. So you're literally just sampling lots and lots and lots of decision trees. To be fair, we did do importance sampling. So we did, start with cart and then sample around the cart solution. But you're not trying to produce how do I say this? I mean, you're just sampling. You're trying to look at all the models. You're not trying to look at just the best model. You're actually trying to look at all the models and compute the fraction of them that are good.
Mm-hmm. And Sahil is asking a follow-up question for this, like what is the default setting for neural network when you try to get your Rashomon curve estimate?
So we weren't measuring. We were measuring on decision trees. So yeah, we didn't sample neural networks. That's not something we tried. You could. We just didn't do it.
So Darius is asking a question, which is, I was wondering, how do you cluster your different methods by increasing level of complexity? Example, a given neural network corresponds to a decision tree of what depth is it linked to VC dimension?
Yeah, so the nice thing about what I'm suggesting is that you don't have to do this. So you can just try different machine learning methods. So for example, logistic regression produces linear models. And neural networks are much more complex than linear models, right? So you know that there's a different level of complexity between logistic regression models and neural networks. And as long as you know that the complexity is different, that's all you need to check whether you're in a setting where you have a large Rashomon ratio. So again, this is just a theory. There's no, it's not a proof or anything like that. But yeah, that's the idea, is that you don't have to know exactly what the complexity is. You just need to know that there are different levels of complexity.
So Sahil is asking, you mentioned interpretable ML for computer vision. Can you talk a little bit more about that?
I could. Let's see. With this topic, pictures really speak louder than words. Let's see if I can grab. Do I have? Okay. Yeah, so I'm just going to bring up a slide really quick. Okay, so this is a project that my student Alina is kind of spearheading, which is to use interpretable neural networks for mammography, for digital mammography. And so this is an example of a lesion. And then the lesion, the question is, how does the neural network sort of analyze this lesion in a way that a physician can understand, right? In a way that a radiologist can understand. So what our method does, and this is not the only method for interpretable neural networks. There's tons and tons of methods out there for this. This is just our particular approach to this problem. So what our method does is it pinpoints parts of the lesion that it thinks correspond to sort of prototype lesions that it's seen before. So for example, it thinks that the boundary of the lesion, like the border of the lesion, looks like this other lesion that it's seen before, and it gives it a similarity score on how similar these are, because it's seeing this and it's saying, this looks kind of like a circumscribed lesion. And so it adds some points to the circumscribed score. And then it also, it looks at all the prototypes and looks at how similar they are. I guess in this case, it's not that much similar to the other prototypes. So it's getting most of its points from the similarity to this prototype. And then all of these comparisons together get added up, and these scores just turn into a total score for some class. So it's kind of showing you, well, I think this looks like that, and I think this looks like that, and then the doctor can decide whether or not they agree with the network. So it's not a sparse model on pixel space or anything like that.
So Benjamin is asking, what missing information do you think is needed to prove the Rashomon curve hypothesis or theory?
I think, okay, so part of the problem is computational, right? We don't have nearly enough computation to actually examine the full function space and try to measure the size of the Rashomon set. So I think in order for the theory to be more solid, I think being able to do that would be really helpful. But of course, I don't want to exhaust the world's computers by trying to prove it. But yeah, I think that's what would prove it. There might be other ways to prove it that I haven't thought of. I'm just telling you the way that we tried.
Right.
Yeah.
So Emily is asking, is there a correlation between accuracy and size of the Rashomon set for different cases? That is, did you find it was the case that the Rashomon set was larger in cases where model accuracy in general on the problem sort of maxed out at a lower accuracy than on problems where a more complex model was able to perform well?
Okay, so that's a really interesting question. I don't know how you came up with that, but it took us, like a year to come up with questions like that. So anyway, as it turns out, if the data set permits models that are very, very accurate, like if you can get 99% accurate, like MNIST, for instance, MNIST, you can get almost 100% accuracy all the time. So in that case, it has a large Rashomon set. So you can definitely max out. When you have a large accuracy, the Rashomon set tends to be large. But for cases where the accuracy is lower, we didn't necessarily find a correlation. So for example, with ImageNet, that's a kind of lowish accuracy case where the Rashomon set is probably really, really tiny. I'm guessing. I'm not sure about this because we didn't check it, but ImageNet, I'm guessing the Rashomon set is really small, and that's a fairly low accuracy. Whereas for like recidivism prediction, that's also kind of low accuracy due to the inherent level of noise in predicting whether somebody will get arrested in a couple of years, right? And there the Rashomon set's quite large. So I don't think there's a direct, you tell me the accuracy, I know the Rashomon set, except in this case where like everything's super accurate.
Right. So Ulrich is asking the question, do you think one can estimate other properties of the Rashomon set more easily without estimating it? For example, range of the feature importance or range of fairness.
Yes. Okay. So this is a great question too. Wow, you guys are really sharp. So we wrote this paper. I'll see if I can locate it. All right. So let me share my screen again. So this paper is called All Models Are Wrong, but Many Are Useful. Learning a Variable Importance by Studying an Entire Class of Prediction Models Simultaneously. So that model does exactly what you're suggesting. It measures the range of variable importance for the Rashomon set. Okay, so that's exactly what it does. So it looks at the I don't know if we wrote that in the abstract, but it looks at all of the good models and measures the range of variable importance on the set of good models. So it does exactly what you're suggesting. And then the question is, what other things can you measure here? Where was that question?
Yeah, it was in the answer. Yeah, it's like fairness, for example. It was also asking like if you could maybe like measure fairness or range of the feature importances.
Yeah, so I don't know how you're measuring fairness, but you could definitely look at the range of fairness measures within models in the Rashomon set. Definitely.
All right, so maybe I'll take one last question and then we can go into talking a little bit about your journey and research. So Marina asks, even when the accuracy of a simple model and the accuracy of a complex model is very similar, the kind of errors could be very different. Maybe simpler models commit more harmful errors. Any results or insights on this?
Yeah, that's a good question. We haven't really studied that. But you could definitely do it. So you could, for instance, weight each of the errors in the loss function, and you could change that loss function so that the Rashomon set actually changes, so that you're actually only looking at models that don't commit harmful types of errors. Yeah, but that's not something that we've tried to do. I think it's a good idea. Yeah.
Okay, awesome. So maybe we'll spend some time in the interest of time talking a little bit about your journey. So Cynthia, if you could talk a little bit about, what your journey was, what your education was, what motivated you to start doing research in machine learning broadly, and the topics that you work on now.
Sure. So, I mean, I was working in machine learning before it was popular. So I was at Princeton before we had even a single professor at Princeton who was working in machine learning. So I I was looking for an advisor, and I went to a nearby lab, and I met someone who I wanted to work with, and that was Gary Flake, and he gave me a book on support vector machines. He gave me Vapnik's book, and I read it, and I thought it was incredible that you could predict the future from the data set. And so I decided I wanted to do that. And so I read the book. I'm not sure I would advise other people to start doing machine learning this way. This was, trial by fire. It was very, very, very hard to read. But I read it, and I was really interested in support vector machines. And so I ended up being a theorist. And so Rob Shapiro ended up coming to Princeton, and he gave me a problem to work on, which was whether boosting maximizes the margin like support vector machines. And so I worked on that for a while, and I was able to prove some really nice tight bounds on the margin that AdaBoost creates. So AdaBoost does not maximize the margin like support vector machines. And so I was able to prove that. And then I was able to prove that how close it gets to a maximal margin, and I had a tight bound on it. It's actually a really interesting kind of U-shaped function with lots of gamma functions and so on. It was a theoretical project. And then after I graduated, I started working on ranking for a while, and then I wanted to use it in the real world, and I had a two-body problem. And so luckily somebody from NEC Labs, Dave Waltz, who I met as a graduate student, offered to hire me to work with a power company at Columbia University to work on ranking, because they were ranking components of the power grid according to their probability to fail. Okay, so I went and took that job, and I was able to use my ranking techniques, but none of them worked. Nothing worked. In fact, none of everything I'd ever learned in machine learning actually worked. Machine learning just didn't work. Nothing worked because the data set was incredibly messy. And I didn't know how to clean data sets. This was before big data. Nobody knew this wasn't a thing. I just got handed this data set, and they were like, do machine learning on it. And I was like, okay. So after like a bunch of false tries where we sent the power company into manholes that were not ready to explode, and they were wondering what the hell we were doing, we finally figured out how to deal with this messy, horrible data set. And then I figured out that, like, even after cleaning the data set, all the machine learning methods perform the same. And then why was I doing this? And so I had kind of a change of heart about what field I chose, and finally just said, well, maybe I should try to make models more understandable, because that's where we were actually getting gains in this power grid project. Like, we could show the power grid engineers the models, and they could say, oh, you're using neutral cables. Neutral cables don't have anything to do with what's going on here. So you probably have an issue with your model. And we, after thinking about it, it's like, yeah, neutral cables really don't predict power failure. They shouldn't predict power failures. So in that case, the reason the neutral cables were in there is because this was a data leakage problem that shouldn't have happened, right? The neutral cables were there after the manhole was replaced. So yeah, after we took the neutral cables out, the models became much more accurate, and we were able to finally predict power failures. So then after that, I ended up just working in interpretable machine learning, because I realized how important it was. And for many years, people would walk up to me and they would just yell at me. I mean, they would be like, you don't need an interpretable model. I don't need this. My black box models are fine. And so it's only in the last few years that it's changed. But unfortunately, this sort of black box models are fine thing, it still is pervading society, because people are now trying to explain black box models instead of just replacing them They're just using more complicated models than they need to. So I've been trying to like deal with that situation more recently. You can see that I've written a paper telling people not to, not to explain black box models for high stakes decisions in particular. Just replace them with models that are simpler and more interpretable.
Yeah.
Yeah. Okay. So that was a long answer, but hopefully got it.
No, that was. Thank you so much for this detailed answer. So I also wanted to just kind of highlight that I think, as you rightly pointed out, you also started working on interpretability before it became popular, right? Like I remember I was looking for sort of like mentors, advisors in like say 2013 when I was like a younger PhD student, and I could see that literally like when I was looking for work in that space, it was mostly your work that came up, right? So like I feel like you and Rich Karwana were the two people who were working on this before it became a fad over the last couple of years. So I think you have a knack of picking problems and entering into areas like before they even become like very popular and caught on. So yeah, like that's something that it's kind of, maybe you have a lot of foresight about these kinds of things, about their popularity and things like that.
Oh,
So you
I wasn't doing it because I thought it would be popular. I was doing it because I wanted to solve my power grid problem.
right, yeah. So in
Yeah.
some sense, real world problems kind of motivated what you need for this, right? I think that's an opportunity that probably many others miss seeing, right? I'm sure like real world problems which required this were always there, but I think very few of you were able to like strike that chord with interpretability. And I could see that, yeah, I think you also encountered some kind of like pushback as to like who really needs interpretability early on, but over time, like everybody started like saying that, oh, of course we need interpretability, there's nothing to question there about. So I was also kind of, I wanted to talk a little bit about, you have been a strong proponent of we should try and use simpler models more and more, especially as you said in like high stakes decisions. But do you feel like, especially for modalities like images or like graphs and some of these like complex high dimensional data modalities, do you think that maybe there's a need where a complex model might be better, and there maybe explainability is a bit justified? Or do you feel that this argument of let's build interpretable models and they are like going to be as accurate as complex models, do you think that is more applicable to maybe tabular data sets or low dimensional? Or do you feel like that argument extends even to other kinds of high dimensional data sets?
I think it's mostly for tabular data that's kind of curated. But for computer vision, the approach that at least I've been taking is that that you can still put constraints on the computer vision models, and you're not losing any accuracy. And those constraints allow people to visually check parts of the model before it goes into a final prediction. So it's at least somehow decomposable into things that people can understand. Uh, yeah. So, but I'm not saying that there's anything wrong with explainability methods. I'm just saying that for high stakes decisions, probably we shouldn't trust them. So, for instance, a number of people have told me that they've tried like lots of different saliency methods
Yeah,
for computer vision problems, and they all produce different results. And so, how much can you really sort of trust those?
those messages.
Yeah, and I think we should go beyond saliency too. I don't think saliency is everything.
Right.
Yeah.
Yeah. Yeah, no, and I think there have also been works like by Julius Adebayo and Bean Kim and so on, which showed that like even if you make random changes to your model or like flip their edges and so on, saliency maps sometimes still don't respond to those changes, like showing that they are like literally generating these things out of random like edge weights and so on, which is problematic. So yeah, there are definitely, I agree that I think I definitely like kind of agree with your general sentiment that wherever possible, why don't we just use an interpretable model right from scratch so that you avoid this additional level of uncertainty or like approximation on top of an existing model, for sure. Yeah. Can you also talk a little bit about like if there's a new student, like a new PhD student, first year, second year, who is trying to enter into this field of like interpretability or more broadly trustworthy ML? What would be your advice to them? Like what should they start doing in terms of their skill sets, learning? How should they approach problems?
Oh, so I'm glad you asked this because I just wrote this document for graduate students, right? I just wrote this thing. I wrote a review paper. Let me share the link to that. And I wrote it exactly for this purpose to answer that question. See if I can locate it. Yeah, here we go. Yeah, so I wrote this review paper. Let's see, how can I send it to the whole?
I
Here we
think you
go.
can
Got it.
put it on the chat. Yeah, to
Yeah,
everybody.
so this is a review paper, and it doesn't completely cover the whole field because it's really a huge field that can touch on a lot of different aspects of machine learning.
Mhm.
But it at least talks about 10 problems that I think are important and other people think are important too.
Mhm.
And it reviews the literature on each of those 10 problems. So it's like a couple of pages on each problem. And
Mhm.
so you can take a look through that and see if any of those problems spark your interest. And if they do, all the relevant literature is right there in each of the sections.
That's amazing. And just curious a little bit more about your research process, given that you started doing machine learning interpretability when it was not even really like a well recognized or like sort of researched topic. So how do you go about picking your problems?
Oh, well, I don't know. You mean the real world problems or the methodological problems?
Or like, let's say you were writing a paper after like 6 months from now. So what would motivate you to like pick a problem and say, oh, this is a great problem. Like, let's pursue this and write a paper on this topic.
Well, okay, so I go through these like theoretical applied waves. I'm just coming off of a methodological wave and doing more applied work. So um, I use the applied work to kind of motivate algorithmic development. And I also like have a lot of collaborators that I really like to work with, including Hima. But I have a lot of like doctors and you know I meet people who are from different who are not machine learning people who are actually trying to solve problems. And I try to work on stuff with them. And then sometimes talking with them makes you realize you need a tool that doesn't exist.
Right.
And then you can try to develop that if you need it.
Got it. And how important do you think is like talking to practitioners, especially like when doing research in this broad area of like fairness or like trustworthy ML or explainability, interpretability?
Well, as I found, right, I was a theorist, and then I went to work with the power company, and I found that all my stuff and everybody else's stuff was totally useless, right? Um, so I think it's good to get started doing that early, so you don't waste a whole lot of time doing something that you later figure out is not actually what you want to be working on. I mean, I can't say I regretted working on these theory problems. I enjoyed them. They were interesting math problems. I learned a lot, but that's not really who I am anymore, right? And that's not really what I work on right now. And it's because of these experiences working on these real problems that I changed.
Right. So I think we are almost hitting at like 1:05 p.m. So basically, what we'll try to do now is take about a 2-3 minute break, assemble back at like 1:08 p.m. On the Zoom link again, and then there'll be a participant-driven discussion where you can talk to each other and also some of us about this talk and also more broadly the field of interpretability. So we break for about 3 minutes now and we assemble back at 1:08 p.m. Thank you so much. Thank you, Cynthia. Thanks a lot for this talk.
My pleasure.